Okay, let's start. Hello, everybody. Welcome to the second lecture of the Global Astrochemistry lecture series from the Big Bang to Life. And so our lecturer today is Professor Barbara Ryden from the Ohio State University, and the topic of the lecture is the Big Bang. Barbara, please.
Oh, thank you for that introduction. Now, before I begin, let me first introduce myself. Now, I'm Barbara Ryden, coming to you live from McPherson Laboratory on the Ohio State University campus. Somewhere in this building, somebody is doing repairs. So if you hear a faint drilling noise in the background, that's not a problem with your speaker. It's something going on in the background. I'll try, of course, to speak distinctly. Also, I realize that I'm fitting a 2-hour time slot. 2 hours is not long to fit in a complete history of the Big Bang and also the early molecular universe, but it is a rather long time to just sit in a chair and listen. So I've built in a 2-minute break in the middle of my lecture, and also there will be time at the end if you want to ask me questions. So don't panic. Now, let me share my screen here. And if at any time you can't see what I'm doing or lose sound or you just have no idea what I'm talking about, you can drop a comment into the chat. So we have somebody here dealing with the technical issues in the background. And if you have questions about the science, of course, you can ask questions during the question and answer period afterwards. So this is a rather daunting topic I've been handed. I realize that. I'm going to first start off by telling you what's the Big Bang, what a molecule is, although I'm pretty sure you have an idea of what molecules are since you're taking this course, and what we mean by the early molecular universe. Now, I am a cosmologist, at least, I pretend I'm a cosmologist for the purposes of writing a cosmology textbook, but remember, it's an introduction to cosmology. So we'll be talking about cosmology at an introductory level with a focus on, how it leads up to all the interesting chemistry present in at least some regions of the universe today. So I don't expect you to be an expert on cosmology. And in fact, I'm going to start out by beginning my talk simply by telling you what we mean by the Big Bang. So the Big Bang theory, in its essence, can be stated extremely simply. That is, the Big Bang theory states that the universe is expanding. That's part of the Big Bang theory. But the second part of the Big Bang theory is that it's expanding from an initial state that was very hot and dense. And this initial state occurred at a finite time in the past. Now, a lot of cosmology deals with trying to quantify these statements. How hot, how dense, how long ago did the expansion begin? But basically, that's the central idea of the Big Bang theory. It distinguishes the Big Bang theory from what was once a popular rival theory, the steady state theory, that stated, yes, the universe is expanding, but it's perpetually expanding with new matter being produced in the intergalactic voids at all times. So the Big Bang theory, it's very important that it's a theory that says things in the past were a lot different than they are now. The universe is much hotter and much denser than it is on average today. I'm emphasizing this point because, well, if you read the science news, you get all these clickbait headlines, astronomers disprove Big Bang theory, and you read the actual article itself, and, they haven't actually disproved the Big Bang theory. They have, modified some small section of what is now the dominant paradigm within the Big Bang theory, that is the lambda CDM model. Lambda CDM says that the energy density of the universe today, right now, even as I speak, is mostly contributed by a cosmological constant, symbolized by the Greek letter lambda, first introduced by Einstein in around the year 1916. So lambda's been around for a while. And the portion of the energy density that isn't contributed by the cosmological constant is contributed by matter. So stuff made up of massive particles. And most of that matter is cold, dark matter, CDM. So lambda CDM is a statement that, from the observations we can make today, it looks like, the ordinary baryonic matter, the stuff of which you and I are made, stuff made of protons, neutrons, and electrons, is actually contributing only a small fraction of the total energy density of the universe today. But that's okay. You don't have to be part of the majority in order to be interesting. And the stuff made of protons, neutrons, and electrons is the portion of the universe that undergoes really interesting chemical phenomena. Which brings me once again to my next admission that, yeah, I'm a cosmologist. I took a course in organic chemistry as an undergraduate, ran away screaming, and ended up in the field of astrophysics, where most matter is extremely low density and therefore undergoes very little by the way of chemistry. So I'm going to give you my simple definition of chemistry. Okay, maybe it's a little too simple, but from the point of view of my lecture today, I'm going to say chemistry is the study of how atoms and ions combine to form molecules, and by implication, how you can rip molecules apart, and what the properties of those molecules are. So, from my point of view, that's what chemistry is. Now, yeah, you're all, I'm sure, more sophisticated chemists than I am, but this is, for the purposes of what I'm going to be talking about today, enough of a definition of chemistry. Now, I also need to define what a molecule is. Now, from the implications of my definition of chemistry, it's something made with atoms and ions hooked together. And here the hooking is done by electromagnetic forces. So for instance, consider carbon monoxide. One carbon atom, one oxygen atom, hooked together by a nice, strong triple bond. So carbon monoxide, I think we can all agree that's a molecule. It's not a molecule you want to breathe a lot of because it grabs onto your hemoglobin and doesn't let go. Not good for life, but it's definitely a molecule. However, consider a hydrogen atom and an oxygen atom bonded together. This is called hydroxyl, and somebody who does chemistry in the laboratory on Earth will probably call this a radical. It's extremely reactive. You get it close to anything and it'll react with all these different atoms. And in particular, if you have a hydrogen atom anywhere nearby, hydroxyl plus hydrogen goes to a water molecule. However, remember that astronomers, when they're dealing with chemistry, it might be chemistry inside an interstellar gas cloud. And at the very low densities typical of even the densest portions of interstellar space, a hydroxyl radical will be around for a very, 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 very long time before it can bump into another atom and undergo a reaction. So astronomers tend to not make a verbal distinction between molecules and radicals in the way that chemists do. So just to give you a heads up, we'll talk about OH and other radicals simply as molecules. And also, if you have, say, a hydroxyl radical to which you add another electron to make a hydroxide anion, molecules that are ionized, that have either an extra electron or an electron taken away, even if it's not electrically neutral. Again, astronomers tend to wave their hands around and say, well, it's all molecules. So when I say molecule, I don't necessarily imply that it's electrically neutral. I don't necessarily imply that it's not reactive. It's just at least two atoms or ions that are bonded together by electromagnetic forces. So, Big Bang and the early molecular universe. That's the title of the talk today. And you get to that adjective early. Cosmologists love talking about the early universe, but they're not always clear on how early they mean when they say early universe. For some cosmology early universe snobs, they snub anything after the first second of the universe. But here, when I talk about the early molecular universe, I'm talking about the universe in what cosmologists call the dark ages. That is the time prior to the formation of the first stars. Now, when the very, very first star formed, we don't know exactly, but we know that stars were forming at least, let's say in round numbers, about 400 million years after the start of the expansion. That is 4 million years after, quote unquote, the Big Bang. So I will be talking about molecules that can form before you have stars in the universe. This distinction is important because, as Professor Olofsson will tell you next week, stars are good at manufacturing lots of different elements, including, but not limited to, the carbon and nitrogen and oxygen that make up the really interesting molecules within our bodies. So, on the one hand, by restricting ourselves to only the first 400 million years of the universe, we get rid of all the complexities of very complex organic chemistry. I'm vastly amused and vastly relieved by that. But as we'll see, without stars, you're kind of limited in the molecules you can make because there weren't very many different elements back then. Still, as we'll see, the molecules you can form early in the history of the universe affect the first stars that you form, and the stars that first form affects the second generation of stars, and so forth. So it's all tied together. Okay, cosmologists. We're kind of unusual people. On the one hand, we like talking about really tiny things, the different individual particles that make up the matter, for instance, but we're also used to talking about very long time scales and very large length scales. So when cosmologists are working, one of their favorite time scales is the gigayear, 1 billion years. In round numbers, about 3 × 10⁻16 seconds. Why is the gigayear an important unit of length for cosmologists? Well, for one thing, it's a useful unit of time for measuring the age of stars, ordinary middle-aged stars like the sun, for instance. The age of the sun, the time that has elapsed since it first started fusing elements in its center, about 4.57 gigayears. And the time that's elapsed since the Big Bang, the start of the expansion of our universe, about 13.7, maybe 13.8 gigayears. So our sun has been around in its current stellar form for about a third the age of the universe. On length scales, although sometimes cosmologists talk about gigaparsecs, the unit of length that they love is the megaparsec, 1 million parsecs. So about 3 times 10 to the 22 meters, if you prefer metric units. Why is the megaparsec a useful unit of length? Well, from where we sit inside the Milky Way galaxy, the distance to the Andromeda galaxy, otherwise known by its catalog number M31, that's the nearest large spiral galaxy to our own large spiral galaxy. It's about 3/4 of a megaparsec. So if you're in a little group of galaxies like our own local group, yeah, the nearest bright galaxy about a megaparsec away. On larger scales, the Coma cluster of galaxies, the nearest really big gravitationally bound cluster of galaxies to us, is amusingly almost exactly 100 megaparsecs away. So think of a megaparsec as a useful unit for measuring the distance between neighboring galaxies, and 100 megaparsecs as a useful unit for measuring the distance between clusters of galaxies. These are the length scales that we're talking about. Now, it's easy for me to say the universe is expanding from an initial hot, dense state to finite time in the past. I've said that sentence so many times it trips off my tongue. But of course, we want to know not merely what we know, but also how do we know that? How do we know the universe is expanding? 1 century ago, in 1924, the idea of an expanding universe was this really bizarre new idea that had just been introduced by, for instance, Alexander Friedmann in Russia. Today, however, the Big Bang theory is a standard part of cosmology. So the realization that the universe is expanding really came about when people had observational evidence for the expansion of the universe. So suppose that you are sitting on a planet looking outward in space using a telescope, and you see a distant galaxy. At visible wavelengths of light, the light from that galaxy comes from the billions of stars that the galaxy contains, and so it has the same absorption lines that you find in the spectra of an individual galaxy. Now, when you measure the observed wavelength of those lines, you're likely to say, oh, wait, the observed wavelength is different from the wavelength for that particular absorption or emission line that you would measure in a laboratory here on Earth. And so there's a wavelength shift due to the expansion of the universe. And since the universe is expanding, here in this 3-panel cartoon going left to right, the universe expands. And as the light travels through the universe, its wavelength is expanded along with the global expansion of space. So the redshift z is a dimensionless number. It's the fractional change in wavelength divided by the wavelength you would measure at rest in your laboratory. And as was first found by Edwin Hubble in the late 1920s, if you can estimate the distance to a galaxy, the light from that galaxy has a measurable redshift z that is proportional to its observed distance. And since the time it takes light to travel that distance is, distance divided by speed of light, the redshift is proportional to light travel time. Now, of course, things get really complicated when you talk about galaxies that are very distant today, since they were closer in the past, and you have to worry about the expansion of space as a function of time. However, for relatively nearby galaxies, those with a redshift z that is much smaller than 1, you find out that distance and the observed redshift are proportional to each other. So for instance, in this slide, the figure on the left, that's pinched from Edwin Hubble's article in 1929. And each of these little dots represents a galaxy. And on the vertical axis, the velocity is just, he's assuming a linear relationship between redshift and velocity, which is a good assumption for these nearby galaxies. Now, Hubble's distances were very, very bad. For instance, all these dots on the right, Hubble thought they were 2 megaparsecs away, but those dots on the right, they're actually all in the Virgo cluster of galaxies, which today is thought to be around 15 megaparsecs away. So his distances were too small by a factor of 7. Fortunately, his distances were wrong by a uniform factor of 7 for most of these galaxies, so he did correctly deduce that there was a linear relationship between distance d and redshift z. Notice there's a lot of scatter. In part, this is due to, bad estimates for distance, but in part it's because there is an intrinsic scatter. Galaxies are not tamely expanding along with the universe because they pull on each other gravitationally. You have nonlinear effects due to their peculiar motion, as it's called. So you want to know, how fast is the universe expanding today? Well, you can encode the speed of expansion by a single number, which is now called the Hubble constant. Edwin Hubble himself did not call it the Hubble constant. No, he had a healthy ego, but it wasn't that inflated. The name Hubble constant, sometimes called H naught, for its little subscript there. So, okay, you measure a redshift, you estimate a distance to a galaxy, you multiply the redshift by the speed of light to get a speed of recession for the galaxy, and then, to make the units come out right and to make the normalization come out right, you have to multiply the distance by this constant, h sub 0. Now, Hubble himself, because he grossly underestimated the distance, grossly overestimated the Hubble constant. But, by the time you get to the 21st century, as in this figure on the right, people had at least a general correct knowledge of how far away galaxies are. So here, zipping forward in time more than 7 decades, people have figured out that, oh yeah, the Virgo cluster, it's farther away than Hubble thought, and people are still trying to fit a straight line. Because of the scatter, we're not sure exactly what the value of the Hubble constant is. And in fact, if you hang out with cosmologists at all, buy them a few beers, and they will start arguing about the value of the Hubble constant. This argument is politely known as the Hubble tension, as some observations indicate that the Hubble constant is around 73 kilometers per second per megaparsec of distance, whereas other observations indicate that it's more like 67 kilometers per second per megaparsec. Now, compared to the uncertainty, even a quarter century ago, you might say, oh yeah, this is a small difference. Nevertheless, you look at the statistical error bars on each of those numbers, 67 versus 73, and yeah, it's a statistically significant difference. It's still unknown why these two techniques give different numbers. It might just be, the boring fact that we don't understand the systematic errors well enough. And this is probably the correct answer. It's certainly where I place my money. However, there is the possibility that there's going to be some interesting new physics buried within this controversy / tension. However, since this is not going to be a talk about the Hubble tension, I'll just say the Hubble constant is 70 plus or minus 3 kilometers per second per megaparsec. I know it sounds like I'm being mushy and refusing to take sides, but as I said, that's enough accuracy for our purposes in this particular discussion. Kilometers per second per megaparsec, kind of Baroque units, but Notice that kilometers and megaparsecs are both units of length. And so if you take 1 over the Hubble constant, that gives you a number that has units of time. And for 70 plus or minus 3 kilometers per second per megaparsec, it turns out to be about 14 gigayears. 14 gigayears. Interesting, though. I told you earlier that our best estimate for the age of the universe is 13.7 gigayears. Suspiciously close to the Hubble time? Well, no, it's not suspicious at all, because if the expansion of the universe were just coasting, with nothing causing the expansion to speed up or slow down, then if you run the film of the universe in reverse, in a coasting universe with no acceleration or deceleration, the time since the beginning of the expansion in its initial dense state would be exactly equal to the Hubble time. So the Hubble time gives a natural timescale for the expansion of the universe. It also, if you work through Einstein's field equations, tells you how dense the universe is today, how much energy there is per cubic megaparsec. And remember, I brought up Einstein, mass and energy are equivalent. So you can talk about a mass density or an energy density just using the usual conversion factor of the square of the speed of light. So you work through all the general relativistic calculations, and you find out that, oh, the curvature of space is linked to the density of an expanding universe. Space will be Euclidean, otherwise known as flat, if its mass energy density equals a critical value. So a Euclidean universe is one in which all of Euclid's laws that you learned in high school geometry hold true. Parallel lines never meeting, the sums of the angles at the corners of a triangle adding to 180 degrees, all that stuff. A Euclidean universe is sometimes called a flat universe, but in that case, you have to put in the subscript, oh yeah, the footnote, that flat in this case does not mean two-dimensional. It just means that Euclid's laws hold. Okay, skipping over a great deal of math, thank goodness. There's a critical density at which space follows the laws of Euclid, and 3 times the square of the Hubble constant divided by 8 pi times big G, the Newtonian gravitational constant. We know big G pretty well, so most of the uncertainty in what the critical density is today comes from the fact that, yeah, there's still this argument going on about the exact value of the Hubble constant. But it comes to about 9.2 times 10 to the minus 30 grams per cubic centimeter. Grams per cubic centimeter, I'm using that as my unit of density because, well, water. Water is 1 gram per cubic centimeter. It's a density that we know really well. So even thin air, the air around us, is 10 to the minus 3 grams per cubic centimeter. So it seems that in order to have a Euclidean geometry, the density of the universe has to be really, really low. The critical density is equivalent to 1 proton in a 200-liter barrel. So yeah, really, really low in density. So if the density is greater than the critical density, then space is positively curved. Its geometry is the 3-dimensional equivalent of the geometry on the surface of a sphere. And positive curvature acts as a magnifying lens. That is, in a positively curved universe, you look at a distant object and it appears larger in angle than it would in a Euclidean universe. On the other hand, if the density is less than the critical density, then, yeah, you guessed that space is negatively curved. And in that case, curvature acts as a demagnifying lens. You look at distant objects, and they are smaller in angular size than they would be in a Euclidean universe. So This is an interesting example of the power of general relativity. You want to know how much stuff is in the universe, how many grams per cubic centimeter there is in the universe of everything. Protons, neutrons, electrons, photons, dark matter, cosmological constant, lambda, lost socks, everything. And you can do it using geometry, just by looking at very distant objects and saying, whoa, they look really big in angle, or wow, they look extremely tiny in angle. I can barely make them out. So we have observations. Astronomers are really good at looking at things that are very far away. It's kind of in the job description. So when you look at distant objects, you find, that they're not unexpectedly large in angle, nor are they absurdly tiny. So on the left here is an example of a picture of galaxies that have a high redshift. Here they're labeled by their individual redshift. And you see they have redshifts, in many cases, very much greater than 1. So they're really far away. And although they get smaller in angular size with greater redshift and thus greater distance, it's the dwindling in angular size is what you would expect just from Euclidean geometry. However, the most distant things you can see directly are the hot and cold spots on the cosmic microwave background. The cosmic microwave background, CMB, I'll be calling it for short, is the leftover light from the early universe, when it was sufficiently hot and dense that all the hydrogen was ionized and the universe was opaque. So as the universe expanded and cooled, it became transparent. The photons were liberated. And those photons that came from compressed, higher density, higher temperature regions, a little bit shorter in wavelength, a little higher in energy, and the regions that came from slightly lower density, slightly cooler regions, are photons slightly lower in energy even today. So on the right, you see the cosmic microwave background. The different colors represent different temperatures. If you kind of squint a little bit, you see, they're spots of a particular size, about a degree across. And the physical size of those objects is known from the physics of recombination of the universe becoming transparent again. And the angular size that we measure for them, well, it's consistent with the geometry of the universe being completely Euclidean. So all of that Euclidean geometry you used in high school, congratulations, you can use it on the universe at large. So we observe that on very large scales, the geometry of the universe is consistent with being Euclidean. Therefore, if general relativity is correct, it's passed all the tests so far, this means that the density of the universe has to be close to the critical density. Cosmologists talk about this, density in terms of a density parameter, omega. It's just the actual density of the universe today, averaged over large volumes, divided by the critical density at which it's perfectly Euclidean. And the value of omega, as I said, consistent with being 1 to within about 0.5%. So we know the density is close to the critical density, but because of the uncertainty in the Hubble constant, we're not sure exactly what that critical density is, but we're working on it. We're working on it. So the universe is expanding today, hat tip to Edwin Hubble. But is that expansion speeding up or slowing down? If gravity were Newtonian, you would say, oh, well, we know that the universe contains matter, and therefore matter always exerts an attractive force on other matter. So if the density were provided entirely by matter, then the expansion would be slowing down. This is true in Newtonian physics, but also general relativity agrees. If the universe contained only massive particles, then the expansion would be slowing down. However, Einstein sort of livened things up, to put it politely, by pointing out that the field equations can include a constant that he called the cosmological constant, and that he assigned the symbol lambda to. So if the density of the universe is provided entirely by a cosmological constant, then the expansion of the universe speeds up with time. So speeding up, slowing down, it's no longer true as it would have been to Newton if he had thought of the expanding universe, that, oh, the expansion has to be slowing down. Well, you can find out whether the universe is speeding up or slowing down. I showed you the results of Hubble and the Hubble light observations from the year 2001. These were all at very low redshifts, much smaller than 1, nearby galaxies. But suppose you go further out in space and therefore are looking further back in time. When you look at galaxies whose light has a redshift of 1 or more, then you're looking back to when the universe was expanding either faster or slower than it is today. And the exact shape of the distance redshift relation becomes nonlinear at large redshifts and tells you what the acceleration history of the universe is. So once this was realized, of course, it was only a matter of looking at very distant objects and accurately determining both their redshift and their distance. Famously, you can do this for a subclass of supernovae, type 1a supernovae, that have luminosities that you can determine, and therefore measure their flux, know their luminosity, compute their distance. So two different groups in the late 20th century started to do this, measuring distance versus redshift. You do have to sit around waiting for supernovae to go off, but the universe is big enough that, over the course of time, you can collect hundreds of supernovae. And the Nobel Prize winning result, as we all know now, is, oh, the universe is actually speeding up its expansion. So here's a group of 580 supernovae whose redshift and distance were measured. The top line is the relation you would find if the universe contained only a cosmological constant and were accelerating, speeding up. The bottom line is what the universe would be if it contained only matter and its acceleration were slowing down. And you realize, neither fits very well. Fortunately, we can turn the knobs. We have this twiddleable problem. You can change the amounts of the cosmological constant and matter as long as the sum adds up to the critical density. And so the solid line there, the best fitting line, omega has to be 1 overall, but here it's 69% lambda at the present day and 31% matter. So lambda CDM, you kind of have a handle on how much lambda there is, how big the cosmological constant and how much matter there is. But remember, the acronym was lambda CDM. Most of the matter is dark matter. So you and I are made up of baryonic matter, protons, neutrons, and electrons. It's actually only the protons and neutrons that are baryons. The electrons belong to the separate class of elementary particles called leptons. Lepton from the Greek word meaning light, baryon from the Greek word meaning heavy. I'm always amused when I go to Greece and find out that the smallest and lightest euro coin, the 1-cent coin, is, it says right there on the label, it's lepton, it's light. So baryonic matter, yay, this is the stuff that we love as astronomers because it absorbs, emits, and scatters photons. And it's the stuff that we love as chemists because, yeah, it engages in chemistry. You can make molecules out of it. Dark matter, well, doesn't interact with photons at all, except gravitationally. Since dark matter has mass, since photons have energy, you do have gravitational lensing effects. So that helps you figure out how much dark matter there is in the universe. And if you want, you can talk to a particle physicist. There are all different types of proposed particles, axions, WIMPs, weakly interacting massive particles, sterile neutrinos, supersymmetric particles of different kinds, black holes of different mass, There's no lack of proposed candidates for dark matter. Problem is, since we can only detect it through its gravitational effects, we still don't know what the individual chunks or particles of dark matter are. So putting it all together, lambda makes up 69% of the universe today by mass or energy. Matter makes up 31%. It looks like baryonic matter provides about 5%, maybe a little bit less, maybe 4.8% of the critical density of the universe today, which means that dark matter, provides a pretty big slice of the pie, over a quarter of the pie chart of what's in our universe today by mass, or equivalently by energy. I'm an astronomer. I'm a big photon hugger, but although photons are really useful in bringing information to us from very far away, they contribute only a tiny fraction of the total mass energy content of the universe. The pie slice for photons on this chart, out of the whole 360-degree circle, it's only about 1 arc minute, and thus is unresolved on the size of my laptop screen. Sorry about that. So, okay, the tiny green slice here, it's a small slice, but it's the portion of the universe that engages in chemistry. So total density of the universe today, remember I said it was about 9.2 times 10 to the minus 30 grams per cubic centimeter. But with an important uncertainty, we don't know the Hubble constant very well. The average density of baryonic matter today, you could call it chemical matter, only 5% of that. So 4.6 times 10 to the minus 30 grams per cubic centimeter. So if we say all the baryonic matter is hydrogen, the simplest of atoms and the most abundant atom today, okay, you take that mass density divided by the mass of a hydrogen atom, and the number density of hydrogen atoms, that's a small number, 2.7 times 10 to the minus 7 hydrogen atoms per cubic centimeter. This would be equivalent to 1 hydrogen atom in, not one of those dinky barrels, but to a big, huge 1,000-gallon drum. So look at that big drum there, and put inside its, think, 1 little hydrogen atom. That's the average density of baryonic matter today, the type of matter that makes molecules. And your first thought is going to be, yeah, that's really dilute, isn't it? How are you going to coax such widely separated hydrogen atoms into forming hydrogen molecules? Well, let's think about it. Suppose the universe today were very simple. Suppose it were entirely hydrogen instead of being contaminated with other elements. Suppose everything were spread out in uniform density instead of clumping up into galaxies and stars. So then suppose that density were 2.7 times 10 to the minus 7 atoms per cubic centimeter. So what I'm assuming is a universe that is homogeneous and isotropic, that favorite phrase of cosmologists. Well, with that number density, you can make a rough estimate of the distance between neighboring atoms, just 1 over the cube root in the number density. That's about 1.5 meters. So one tiny little hydrogen atom, and the nearest neighbor is 1.5 meters away. So hydrogen atoms are separated by a distance very large compared to their size. Again, let's quantify this. You have a hydrogen atom, it's surrounded by an electron cloud. The electron's probably in its ground state, so the size of the electron cloud, let's say it's about a Bohr radius across. And so we can say an atom collides with another atom, that is, it will interact electromagnetically at a significant level if the two nuclei come within, twiddle 2 Bohr radii of each other. So twice the Bohr radius, about 10 to the minus 8 centimeters. And if you've done a mean free path problem, you can see where I'm going here. You have objects that are very far apart from each other, but they have a non-zero cross-section for collision. So in this case, let's suppose everything is spherically averaged. So the cross-section for collision, pi r squared, 3 times 10 to the minus 16 square centimeters. So I'm using centimeters, not megaparsecs, because I wanted a small unit of length, but even in centimeters, the cross-section for 2 hydrogen atoms to collide with each other is very tiny. So, mean free path problem, as I said. What's the average distance between collisions, or the mean free path? So if you know the number density of hydrogen atoms, and we've said it's the average density of hydrogen today, smoothing things out, times the cross-section, and measured in atoms per cubic centimeter, the density today is a small number. Measured in square centimeters, the cross-section today is a small number. And so that means the mean free path is this immense number of centimeters, about 10 to the 22 centimeters. Okay, let's convert that to megaparsecs, our go-to distance for very long distances in the universe. And you say, okay, it's only 0.0034 megaparsecs, but even that's a large number. It's about equal to 40% of the distance from here on Earth to the galactic center. So think about it. If all of the atoms in the universe today were uniformly spread out, each atom would travel about 0.003 megaparsecs, about 3 kiloparsecs on average, before colliding with another atom. So wouldn't exactly be high-speed chemistry going on. And in fact, you can convert the mean free path into a time between collisions if you make an assumption about how fast the atoms are traveling. So, okay, we've assumed that all of the gas in the universe is at a uniform density. We might as well say it's all at a uniform temperature too. In that case, the RMS atomic speed, linked to the sound speed of the gas, goes as the square root of kT over the mass per particle. Okay, and I'm just scaling to a temperature of 1,000 on the Kelvin scale. If it were very, very much hotter, the gas would be collisionally ionized. If it were very, very much cooler, then nothing would happen at all. But at 1,000 Kelvin, all those atoms are trucking around at an average, or rather an RMS speed of about 5 kilometers per second, 5 times 10 to the 5 centimeters per second. So, drum roll, please. Typical time between atomic collisions. That's the mean free path, typical distance traveled between collisions divided by a typical speed, the RMS thermal speed of the atoms. And putting in the numbers that we found so far, Oh, 2 times 10 to the 16 seconds. Nearly 1 gigayear between collisions. So if the universe today were homogeneous and isotropic, then if its temperature were 1,000 Kelvin, you would have about a gigayear between one atomic collision and the next collision by the same atom. And of course, lower the temperature of the gas and the timescale becomes even longer. So at the mean density of atomic gas in the universe today, chemistry is, oh God, just so excruciatingly, boringly slow. Oh my God. Well, what can we do to speed things up? Obviously, for atoms to interact, to form molecules, to undergo interesting chemistry on any reasonable timescale, like a timescale very short compared to the age of the universe, they have to be at a density much greater than 1 atom in a 1,000-gallon tank. Well, fortunately, for the sake of chemists everywhere, we live in a universe that is not homogeneous and isotropic today. Lower right, I'm showing you the results of a computer simulation, the Millennium simulation it's called, in which you let gravity work on dark matter and baryonic matter so that it forms structures. Long filaments, superclusters, smaller lumps of matter called clusters, and within clusters you form galaxies, within galaxies you form stars. So most of the volume of the universe today is filled with voids, very diffuse, low density stuff. The gas is all photoionized by all those bright stars sprinkled throughout our universe, and you have no molecules. It's just too low in density for chemistry to go on. So all the chemical action is within all these relatively small bright knots. These are where galaxies are clustering together. And these are the dense regions where you have the possibility of molecules forming. Not the absolute necessity of molecules forming. Within a cluster of galaxies, most of the gas is, again, ionized and at relatively low densities. So let's stop and think. Let's look inside our own galaxy today. Where are you going to find molecules present today within our galaxy? Well, one place you find it is in the interstellar gas within the coldest, densest regions of interstellar space. So within molecular clouds, you find cold cores, and you'll learn a lot more about these molecular cloud cores later in the course, but I'll just give you a few numbers. The number density of hydrogen atoms within these molecular cloud cores, maybe 1 million molecules per cubic centimeter, or 1 million atoms, 1 million individual gas particles. They're called cold cores because their temperatures are quite low, 20 Kelvin, 15 Kelvin, sometimes as low as 10 Kelvin or even 8 Kelvin. But just take this number, density, and temperature, compute the time between collisions for an atom, it's only an hour. Okay, you say, rubbing your hands together. An hour, very short compared to the age of the universe. Possible chemistry going on in these regions. Another place where chemistry is known to go on is, within planets or exoplanets that have nice dense atmospheres. Breathe in, breathe out. You're breathing in and out nitrogen molecules, oxygen molecules. And so within the atmosphere of our own wonderful planets down near sea level, density of about 3 times 10 to the 19 molecules per cubic centimeter. Temperature, again, I'm assuming you're not sitting outside in the cold, nor are you in the sauna, let's say around 300 Kelvin for a typical atmospheric temperature on Earth. And here, this comes to a time between collisions of a nanosecond, a billionth of a second. So you're sitting, you're breathing, the air around you seems boringly still, but the individual molecules are colliding a billion times per second. So at that rapid rate, yay, you can have a lot of interesting chemistry going on inside planetary atmospheres. So today, you look for chemistry, the formation of molecules. It's going to be in the very dense regions, and dense and also relatively cold. So atmospheres of planets, yep, that checks the box. Cold interstellar gas, yep, that checks the box. So today, only these really odd, very tiny places in the universe have high baryon density. But in the past, the entire universe had high baryon density. Because, the whole universe is expanding. And the way we quantify the expansion is, say, pick 2 points in the universe, and the distance between them increases proportional to a scale factor A. The scale factor A is a function only of time. So we're saying the universe is expanding homogeneously. The expansion is the same in all locations, and it's expanding isotropically. You can write the scale factor just as a single scalar function. It's not a matrix that tells you there is shear or that the expansion is different in different directions. So homogeneous and isotropic, the cosmologists love it. And we normalize it so that A is at the present time, right now, T sub 0. And as time expands, as time increases from left to right on this plot in the lower right, the scale factor increases. How fast it increases depends on what's in your universe. In an empty universe, no forces are acting, there's no speeding up or slowing down. The scale factor increases linearly with time. In a universe containing only a cosmological constant, constantly accelerating, constantly speeding up, you get exponential increase in the scale factor. If you have matter in your universe, the gravitational force between the matter causes the expansion to slow down. And if you have only radiation, only photons in your universe, Einstein says, well, gravity works on energy as well as on matter. And as it turns out, if you have only photons in your universe, the acceleration slows down. And the deceleration in this case, is even greater than in a matter-only universe. So in the past, no matter what's in your universe, scale factors were smaller than they are today, and thus, because everything was crammed closer together, the density of the universe was higher in the past than it is now. So if you have some type of particle that is conserved, the number density must decrease as the universe expands. If particles are massive, this includes massive particles like protons and neutrons and electrons. Okay, the mass per particle is constant. It is what it is. And so the mass density decreases as 1 over the volume, or 1 over the cube of the scale factor. For massless particles, like photons, the energy per photon decreases as 1 over the wavelength, and thus energy per photon decreases as 1 over the scale factor. So you get a double whammy for a radiation-filled universe, one with only photons. The photons are diluted, so their number density goes as 1 over A cubed, and the energy per photon goes as 1 over A. So the whole energy density falls off more rapidly as 1 over A to the 4th power. Now, today, most of the photon energy in the universe is provided by the cosmic microwave background. Those poor stars, they've been glowing away for over 10 billion years, but still, most of the energy density in photons is in the form of the cosmic microwave background. I call it mostly harmless because the cosmic microwave background is low in temperature. So the individual photon energy is very small. Cosmic microwave background, discovered by Penzias and Wilson in the 1960s. Its temperature has been measured quite accurately from orbiting satellites as 2.7255 Kelvin. That means the peak of its spectrum comes at 160 gigahertz. And the energy per photon, it's so tiny, only 2/3 of a milli-electron volt. On the other hand, there are plenty of them. The number density of photons in the cosmic microwave background, it's just a black body, so you can compute it, 411 microwave photons per cubic centimeter. Okay, so on the one hand, there are a lot of cosmic microwave background photons. Remember, the baryons per cubic centimeter, if you take the average today, less than 3 × 10⁻⁷, the number of photons over 400 per cubic centimeter. And so the ratio of baryons to photons, there's less than 1 baryon per billion photons today. We're outnumbered, I tell you. However, although the baryons are badly outnumbered by photons, the photons of the cosmic microwave background are very, very, very low in energy. That's why I call them mostly harmless. They're not enough to ionize an atom. They're not enough to trigger any sort of chemical reaction. So from our point of view, the cosmic microwave background today, it's really boring. However, now, I want to leave you something to chew on before we take our 2-minute break. So a few more slides here. Let's travel back in time to when the scale factor was very tiny, less than a part per 1,000. So I'm going to specify an oddly specific scale factor, 7.2 × 10⁻⁴. This was the scale factor in our own universe when it was about 250,000 years old. So we go back to smaller scale factors. At that small scale factor, the photon energy in the cosmic background was very high, high enough to photoionize hydrogen. So here, the arrow of time goes from left to right. I'm plotting it as a function of the redshift of light from that era. That's just 1 over the scale factor -1, because of the way the scale factor and redshift are defined. So here, going left to right, you're going from high redshift to low redshift, from small scale factor to big scale factor. And at a scale factor of 7.2 × 10⁻⁴, or a redshift of 1,380, the ionization fraction of hydrogen was exactly 1/2. So that's where that oddly precise scale factor of 7.2 × 10⁻⁴ comes from. Earlier on, smaller scale factor, hotter cosmic background, more energetic photons. The hydrogen was completely ionized. But as the universe continues to expand, the energy per photon drops. And finally, at last, even those few photons way out in the exponential Wien tail of the black body spectrum don't have enough energy to ionize hydrogen. So the hydrogen in the universe went from being mostly ionized to mostly neutral at a scale factor of 7.2 × 10⁻⁴. That corresponds to a temperature for the cosmic microwave background at 3,800 Kelvin, about the temperature of an M star for the astronomers out there, and the energy per photon about an electron volt. So although today the cosmic microwave background is mostly harmless, back then was not completely innocuous. The photons had enough energy out in the veen tail at least, to ionize the baryonic matter. And the baryonic matter back then, higher in density by a factor of 1 over the scale factor cubed, oh, they were packed in about 720 per cubic centimeter. So at the time of hydrogen recombination, when the ionization fraction dropped below a half, when the hydrogen became predominantly neutral, the mean free path of the hydrogen atoms, oh, okay. Back then, it was about half an astronomical unit. And I realize that's a very anachronistic term, since the astronomical unit is half the distance from the sun, which didn't exist back then, to the Earth, which didn't exist back then. But, we live on Earth. We know what an astronomical unit is. The speed, okay, temperature of 3,800 Kelvin. So the atoms were zipping around at a speed of about 10 kilometers per second. And so, whoops, the time between collisions back then, about 3 months, when the universe was 250,000 years old. So possibility of chemistry because of the relatively frequent collisions. However, this is immediately after hydrogen recombined. As the universe continued to expand, the number density of hydrogen atoms continued to drop, and the temperature continued to drop. So you have hydrogen atoms more diluted and at a lower speed. So it looks like time is working against you in the early universe. As soon as you have enough neutral hydrogen atoms that you can think of making molecules from them, the rate at which they collide with each other continuously drops. So, yeah, doesn't look good. However, when we look at the cosmic microwave background with its hot and cold spots, we are looking at the universe when it was still partially ionized and still opaque. At that time, it was very nearly homogeneous and isotropic. I talk about hot and cold regions of the universe back then, but in fact, the differences in temperature were about at the level of 1 part in 100,000. So the universe back then, when the hydrogen was just starting to recombine, was really boringly homogeneous and isotropic. It's only when you get to later times, when we see how molecules form during the dark ages, the time between recombination of hydrogen and the formation of the first stars, we need to know how those initially very slightly overdense regions collapse to form very bound, dense regions, dense enough and cool enough simultaneously that chemistry can happen, that molecules can form. But first, we need to look at the elephant in the room. I've been talking about elements and saying, well, let's look at hydrogen. It's the simplest and most common elements. But there's a whole periodic table of elements out there. So what about elements other than hydrogen? How do they enter the picture? Leaving you to contemplate the periodic table, the elephant in the room, it's time for a quick break. So we all need to yawn and stretch a little bit. Oof, oof, oof. Okay. Hope you have all gotten yourself something to drink or fulfilled your other bodily needs. I was looking at the chat, some really interesting questions there, and I'm hoping to get back to them at the end of the lecture. But if you have a question that's not answered in the second half, we can circle back to it. But first of all, okay, I acknowledge that elements other than hydrogen exist. We have one interesting sample of matter in the form of our sun. And I've been talking to Mark Pinsonneau, my colleague here at Ohio State, and he has some interesting numbers. He says that the sun formed from the protosolar nebula, a region of gas in our galaxy, when the universe is about 9.2 gigayears old. Comes from the pretty well-known age of our universe plus the well-known age of our sun. And the sun formed from material that was 71.1% hydrogen by mass, 27.4% helium by mass, which means that everything else on the periodic table, do a quick subtraction here, contributed 1.5% of the mass of the protosolar nebula from which the sun formed. And the everything else was in order of mass: oxygen, carbon, neon, iron, nitrogen, and a whole bunch of other stuff, but in smaller and smaller quantities. Now, the material from which the sun formed was enriched or polluted, choose your adjective, with material from previous generations of stars. So during the Dark Ages, that is the era before the formation of the first stars, the amount of hydrogen by mass was 75.3%. The amount of helium by mass was 24.7%. And you do the subtraction there, and that pretty much adds up to 100%. The only other element present during the Dark Ages was lithium, which provided 0.000003% of the mass. So it looks like stars are good at converting, well, pretty good at converting hydrogen into helium, and also, as a byproduct, making oxygen, carbon, neon, iron, nitrogen, etc. Now, once again, this is a situation where I am making an assertion. If you want to know how we determine the abundance of the sun at the time of formation, we can go into that. But of course, I have to stick to the Dark Ages. That's sticking to my lane here, talking about the early molecular universe. How do we know what the chemical composition of the baryonic matter of the universe was before the first stars formed? Well, this is tied into the story of Big Bang and nucleosynthesis. And if you haven't read Steven Weinberg's The First 3 Minutes, it's a really good yarn. It's a story of, well, as it says in the title, the first 3 minutes of our universe. So how did nuclei become synthesized in the early universe? Well, let's go back to when the universe was less than 1 second old. That is, it had been expanding for less than 1 second from its initial extraordinarily hot, extraordinarily dense state. Now, when the universe was less than 1 second old, the cosmic background radiation was, as you might expect, really hot. It was hot enough that the energy per photon was way beyond what you need to photoionize hydrogen, and it was in fact enough to photodissociate nuclei. So an amusing rule of thumb is that the thermal energy, temperature times Boltzmann constant, in the early universe was 1 MeV divided by the square root of the time in seconds. So hey, you want GeV, you want TeV, you want PeV, sure, just go far enough back in time and you can find the energy of your choice. But a few MeV is enough to photodissociate most nuclei. So in the first second of the universe, when the photons were energetic enough to photodissociate nuclei, you didn't have nuclei. You had free protons and free neutrons, and enough free electrons zipping around to make the baryonic matter neutral. Now, you don't see many free neutrons today. That's because free neutrons are unstable to beta decay. A neutron, as shown on the left, can decay into a proton, but electric charge needs to be conserved, so an electron is emitted as well. However, the electron quantum number needs to be preserved, so an electron antineutrino is also emitted in this decay. This decay is possible because the difference in rest energy between a neutron and a proton is about 1.29 MeV. This is greater than the rest energy of an electron plus a neutrino added together. The electron is about 0.51 MeV, and the electron neutrino on this scale is approximately bupkis or diddly squat or nothing, approximately. So the lifetime of a free neutron before decaying, 880 seconds, about a quarter of an hour. So the universe has been around for a lot longer than a quarter of an hour. So free neutrons always decay on a short time scale. But when the universe was less than a second old, neutrons hadn't had time to decay in any significant number. So you had neutrons in the early universe because the universe was younger than the lifetime of a free neutrino, of a free neutron. Excuse me. Also, because the energy of particles was so great, photons had enough energy to create electrons and positrons by pair production. So a 1 MeV photon interacting with another 1 MeV photon is energetic enough to produce an electron-positron pair. Of course, the electrons and positrons can then annihilate to form gamma rays, high-energy photons, but you have this continuous interplay. The photons, the positrons, and electrons are all coupled together. In addition, at times less than 1 second, the neutrino cross-section for interaction, which is a function of neutrino energy, was sufficiently large, and the density of the universe was sufficiently high that neutrinos were still coupled to the baryonic matter. So, for instance, neutron plus electron neutrino goes to proton plus free electron, or vice versa. Or neutron plus positron goes to proton plus electron antineutrino, and that reaction too can go in reverse. So you have this wonderful mix of photons, positrons, electrons, neutrons, protons, electron neutrinos, electron antineutrinos, all interacting with each other at a frenetic rate. So you had a situation, in which everything was in thermal equilibrium. Now, we love equilibrium interactions because, yeah, you guessed it, it makes the math easier. You can, for instance, apply the nuclear equivalent of the Saha equation. If you've ever played around with the Saha equation, it's not just for ionization states of atoms, it's also for dissociating and regenerating nuclear particles as well. So at sufficiently high temperatures, that is when the mean thermal energy was greater than about 0.8 MeV, just works out to that number, neutrons and protons were in equilibrium. In this equilibrium state, you can compute the neutron to proton ratio. Well, it depends upon the neutron to proton mass ratio, but that's very close to 1. It's so close to 1, let's ignore it. And it depends upon the energy difference between the neutron and proton. I just told you that's 1.29 MeV divided by the temperature multiplied by the Boltzmann constant to express it as an energy scale. So basically, as the universe expands and cools, T goes to 0, and you get the neutron to proton ratio as e to the minus an increasingly large number. So the neutron to proton ratio, shown here in this plot, decreases with time as the temperature drops. Now, if the neutrons and protons remained in equilibrium, as you see here, the solid line plummets down to something very close to 0. But what happened is at a temperature of about 0.8 MeV, the neutrino cross-section becomes so small that they say, oh, we're not going to interact with you anymore. So that's when the universe basically becomes transparent to neutrinos. They go just streaming through the universe, bye-bye, refusing to play with anybody else. And so once neutrinos no longer interact, you have a freeze out of the neutron to proton ratio. And given the neutrino cross-section and the difference in rest energy between a neutron and proton, it comes out to a number smaller than 1, but significantly greater than 0. You get about 1 neutron per proton once the neutron to proton ratio freezes out. And it remains 1 neutron per proton until the neutron starts to decay. So when Big Bang nucleosynthesis began, during the first 3 minutes of the universe, there was 1 neutron for every 5 protons. So the first step in Big Bang nucleosynthesis, BBN, is the creation of a deuteron. That is a heavy hydrogen nucleus, also given the symbol D for deuteron. Okay, a proton plus a neutron combine to form a deuteron. Energy is released. This is the binding energy of the deuteron. It's about 2.22 MeV, and it's carried away by a gamma ray photon. Lovely little nuclear reaction. Notice there are no neutrinos involved. You don't have to worry about the weak nuclear force. You just bring the proton and neutron together. There's no Coulomb barrier between them. The neutron has no electric charge. And so you say, yeah, this reaction, proton plus neutron, becomes a deuteron with the photon carrying away the excess energy. This is a reaction that should go like a house afire, as the saying goes. It should go very rapidly. No Coulomb barrier between the proton and neutron, no need for the weak nuclear interaction. Yeah, if you could make deuterons this way today, wow, nuclear fusion would just be a breeze. Unfortunately, yeah, we live in an old universe where all the free neutrons have decayed away. So, lowest order fusion goes on between protons and neutrons until you've used up all the neutrons. But there's an interesting twist, because once you have enough deuterons made, the deuterons themselves can undergo a fusion reaction with other particles present. So the next step, going from deuteron with 2 nucleons in its core, you go to a nucleus with 3 particles in its nucleus. So a deuteron plus a proton makes helium, 2 protons, but only 1 neutron. So it's light helium, helium-3. This is an exothermic reaction, so more energy is carted away by a gamma ray. Or a deuteron can collide with a neutron to make tritium, heavy hydrogen. I mean, really heavy hydrogen, the unstable kind. So hydrogen-3, this is also an exothermic reaction. More energy is carted away by the gamma ray. It is true that tritium is unstable. It decays into helium-3, but its lifetime is 18 years. So as far as Big Bang nucleosynthesis occurs, which happens on timescales of twiddle 3 minutes, tritium can be treated as immortal. So on the one hand, deuterium proton has a Coulomb barrier that drives down the rate. On the other hand, as neutrons are being gobbled up and making deuterons, there are fewer neutrons around. So you make a mix of both tritium and light helium. Next step, well, you've got tritium. You can add a proton to it, and that makes helium, 2 protons plus 2 neutrons, good old-fashioned ordinary helium-4. Or if you've got light helium, if you can add another neutron to it, you make helium-4. Again, more exothermic reactions here, so more energy being carried away by a gamma ray. All of these reactions do not involve the weak nuclear force. They all run very rapidly once you overcome the Coulomb barrier, if you're banging 2 charged particles together. So, lowest order, the simplest description of Big Bang nucleosynthesis is you run rapidly to making helium-4 until you've used up all of the free neutrons. After that, it's almost the end of the line once you reach helium-4. There aren't any stable nuclei with atomic mass 5. That is, if you try to add another neutron to helium-4 to make helium-5, that's wildly unstable, it falls apart. If you try to add a proton to helium-4 to make lithium-5, wildly unstable, it falls apart. If you try to fuse 2 helium-4 nuclei together, that gives you beryllium-8, wildly unstable, it falls apart again. The only stable isotope of beryllium, the kind you find in emeralds, that's beryllium-9. That's another story. Now, if you look at the complete network of possible fusion reactions, as shown on the right here, it is possible to make teeny tiny amounts of lithium-6. If you fuse helium-4 with deuterium, that gives you lithium-6, a nice stable isotope of lithium, and also an exothermic reaction. If you fuse helium-4 with hydrogen-3 or tritium, you get lithium-7, also a nice stable isotope of lithium. It's also possible to get very small amounts of beryllium-7. Helium-4 plus helium-3 goes to beryllium-7, which is, again, an exothermic reaction. Beryllium-7 is unstable. It does later decay to lithium-7 by electron capture. But, it doesn't immediately fall back apart again like helium-8 does. So you have these small amounts of 2 isotopes of lithium plus an isotope of beryllium that eventually decays to lithium-7. But Big Bang nucleosynthesis is a race against the clock. All the time it's happening, the temperature is dropping, the density is dropping, and so your reaction rates are falling off a cliff eventually. Once you get to lithium and beryllium, the densities are so low that you can't go beyond. So there's really no significant amounts of boron, carbon, or later elements in the periodic table. You just run out of time. So Big Bang nucleosynthesis is a sufficiently simple process that you can model it on the computer. Can't do it by hand on paper, I'm afraid. But once you know all the relevant reaction rates well enough, you can do a simulation. And here's a nice simulation done by Alain Koch. Mass fraction of each of these different elements, plus free neutrons, as a function of time. So you start out with protons and neutrons, free protons and free neutrons. You start making deuterium. But notice, once you make enough deuterium, you rapidly go all the way to helium-4. So when I say, yeah, the basic result of Big Bang nucleosynthesis is you make helium-4 until all the neutrons are used up. That's close to true. However, you do end up with deuterium and a little leftover light helium, a little leftover tritium, which will, off to the right, decay into light helium. The neutrons eventually decay away. You get the beryllium-7, which converts to lithium-7, and you get this itty-bitty trace of lithium-6. Notice by the right-hand side of this plot, 50,000 seconds, about 13 or 14 hours. It's all over, aside from the decay of the free neutrons. So a lot of action packed into a very short period of time, with the greatest activity happening when the universe was about 180 seconds old or 3 minutes old. So XKCD usually says it best. Half an hour after the Big Bang, this would have been the periodic table of the elements. And once beryllium-7 decays to lithium-7, you kind of revert to a universe in which you have only 3 elements. Not very exciting during the dark ages, chemically speaking. You have only 3 elements to play with, but you still get to do a little bit of chemistry. But not right away. After Big Bang nucleosynthesis, you get hydrogen, some of which is in the form of deuterium. You get helium, some of which is in the form of light helium, and you get a bit of lithium. However, it's all highly ionized. You don't get molecules forming until recombination occurs. Once you have an ion with at least 1 electron bound to the central nucleus, then you have the possibility of, maybe 2 nuclei can share an electron. So no chemistry until recombination. So nice annual reviews of astronomy and astrophysics article by Gali and Pala shows the now recombination history of the universe without my kindly fiction that only hydrogen existed. Yes, you can compute that initially highly ionized hydrogen converts into neutral atomic hydrogen at a redshift between 1,000 and 2,000, but you can also compute the time of redshift for deuterium. No surprise, close to the time of recombination for ordinary hydrogen. There's not a strong isotopic shift, but you can compute recombination for helium. And in green, I'm afraid the color doesn't show up too well, but green is lithium. So notice the first recombination that you have, as the arrow of time goes from left to right, is the recombination of lithium plus 3, that is a naked lithium atom, to lithium plus plus. And then lithium plus plus goes to lithium plus very soon after. Notice, however, you never get a large amount of neutral lithium in the early universe. There's always enough high energy photons around to keep the lithium singly ionized. Helium, okay, helium becomes mostly neutral at, let's see, a redshift of around 2,500 or a scale factor of 4 times 10 to the minus 4. And as we already saw, hydrogen becomes mostly neutral at a larger scale factor, 7.2 times 10 to the minus 4, or a redshift of around 1,380. So lithium gains 1 electron, lithium gains a second electron, helium gains 1 electron, helium gains a second electron, and then hydrogen gains its electron in that sequence. So the first molecules formed before hydrogen recombination. And just to freak you out, the first molecules that formed in the universe were helium hydride. Helium hydride. Now, when I first heard the phrase helium hydride, I pretty much panicked and freaked out because helium forming a molecule, you can't do that. Helium's a noble gas. I mean, I was completely chemically naive. I knew that you could kind of coax xenon, a very massive noble gas, into fusing with fluorine, a highly reactive element, to make, what is it? The xenon hexafluoride. But getting helium to make a chemical element, a chemical molecule, I mean, how can you do that? Well, let's go back to a redshift of 2000. Hydrogen was still ionized. The helium was neutral by that point. And so helium plus, okay, hydrogen plus, that is to say a free proton plus helium, formed helium hydride plus. This is an exothermic reaction. Okay, that's key. And it emits a little energy in the form of a photon. But yeah, helium is the most noble of the noble gases. How do you coax helium into sticking around with a proton sharing their electrons? It seems pretty odd, doesn't it? Well, I'm assured that helium hydride, otherwise known as helonium, is a thing. Basically, as I mentioned earlier, lithium plus was around. In theory, you could make lithium hydride, but lithium was so scarce. Now, 0.000003% of the baryonic mass in the universe. So if you have a helium atom floating around and a free proton floating around, the free proton is way more likely to encounter a helium atom than a lithium plus ion. And helium plus a proton, making helium hydride, is stable only in isolation. It's extremely reactive. It's the strongest known acid. So it's saying, please, I don't really want to be bound to this proton. I will give it away to whoever asks. Now, the helium atoms, they don't want it any more than the helium hydride molecule wants to have it. So that reaction isn't going to happen. And so if you have helium hydride, it's only present in the extremely low density of space. It's really hard to study in an earthly laboratory, or so I'm told. I'm just a simple cosmologist. Now, there was a Nature letter saying, oh, we have detected helium hydride. It has a very distinctive fine structure line at 149.1 microns, so you can detect it under the right circumstances. But once hydrogen starts to recombine, recombination starts at around 1500, is half finished at a redshift of 1380, pretty much finished by the time you get to a redshift of 1100. Once you have neutral hydrogen atoms, then, here this plot once again from the review article says, whoosh, you very, very rapidly get molecular hydrogen as the most abundant molecule. And you get, hydrogen bonding with deuterium. You get positively charged H2+, and here the green line, hard to see, is helium hydride. So technically, yes, helium hydride was at one point the most abundant molecule in the universe, way over here on the left, before hydrogen starts to recombine, but it quickly becomes overwhelmed by molecular hydrogen. So helium hydride, really freakishly weird, wonderful trivia point, but never contributes significantly to the molecular content of the universe once hydrogen starts to recombine. Now, you make molecular hydrogen actually by a two-step process. Hydrogen atom plus free proton becomes a positively charged hydrogen atom. It then collides with a hydrogen atom, transfer of the electron, so that you form a neutral hydrogen atom plus another free proton flying off into space, now ready to start this whole process over. So you can't simply bang two protons together and form hydrogen. You need to have at least one atom, but you can't simply bang two hydrogen atoms together to get a hydrogen molecule. You have to have both free protons and free neutral hydrogen atoms present to make molecular hydrogen. And as you see here, by a redshift of about 30, not too long before the first stars formed, the ratio of molecular hydrogen to atomic hydrogen froze out at a ratio of about 1 molecule for every 10 million individual atoms. So yes, you can make molecules during the dark ages, during the era before stars formed, but it looks like this horribly inefficient process. And two, all you get out is molecular hydrogen. I have nothing against molecular hydrogen, but it's not really the most exciting molecule in the world. However, this boring result, only a few molecules and they're all molecular hydrogen, assumes uniform baryon density. So this is where we go back to the fact that, the universe tends to clump up with time. At the time of recombination, yes, it was very uniform in density, and therefore molecules will be scarce during the dark ages unless, here's the qualifier, unless those very low amplitude overdensities at the time of recombination became extremely dense. High density regions means high density of atoms, means more frequent collisions between atoms and ions, means more rapid creation of molecules. So cosmologists love to talk about the Matthew effect, that regions that are originally slightly overdense, a little denser than average, become denser with time. Regions that were originally slightly underdense, a little less dense than average, tend to become less dense with time. It's called the Matthew effect. It's a biblical reference in the book of Matthew. For unto every one that hath shall be given, and he shall have abundance. But from him that hath not shall be taken away even that which he hath. Okay, in the archaic English of the King James Version, it's a little bit hard to understand. Let's go to Billie Holiday. She sang it better. Them that's got shall get, them that's not shall lose. So the Bible says, and it still is news. Or in short, the rich get richer and the poor get poorer. Seems to be a truth of many human societies, but it's also a truth of the instability of an attractive inverse square law force. So let's go back in time. Not too far back in time. Big Bang nucleosynthesis is over. We have hydrogen, helium, and lithium. Recombination is over, so we have neutral atoms around. And consider a region that's denser than average. So we can express this as a fractional overdensity. If omega bar is the average matter density of the universe, the actual density rho at any particular place doesn't have to equal the average. It can be a little bit denser than average. And that gives you this fractional overdensity delta. Difference in density divided by average density. So in overdense regions, delta will be greater than 0. But if it's just a little bit overdense, it'll be a small number. Maybe a 10th, maybe 100th, maybe 1,000th. So at a scale factor, very early in the history of the universe had its energy density dominated by radiation. Remember, there are lots of photons today, but very low in energy. In the past, the photons would have been higher in energy, they would have dominated the energy density. So in a universe dominated by relativistic particles like photons, you never get very large density fluctuations. The random high-speed motion of photons in all directions, they have to be high speed, they have to travel at the speed of light, tends to smooth out any density fluctuations. So in the very early universe, when photons dominated the energy density, it had to be uniform in density. At recent scale factors bigger than about 7.77, the universe is now dominated by the cosmological constant lambda. And during a lambda-dominated era, you start to accelerate faster and faster and faster and faster, and that rapid acceleration pulls apart dense regions that aren't tightly gravitationally bound. So basically, things that haven't collapsed by the time lambda dominates will never collapse. So radiation-dominated era, early in the history of the universe, off to the left, you don't get growth in density fluctuations and amplitude because the streaming motion of photons smears everything out. And during the future lambda-dominated era, you don't get growth in density fluctuations because the hyperactive, accelerated expansion of the universe pulls apart everything that isn't tightly bound already. So it's only during this intermediate era, the matter-dominated era, that you can get growth in the amplitude of density fluctuations. I suppose you could call the matter-dominated era the Matthew era, since that's the only time in the universe when gravity works to make overdense regions very much denser and underdense regions very much less dense. So this range in scale factors, corresponding to a range in ages for the universe, is the matter-dominated phase. And during that time, density fluctuations grow in amplitude at the same rate that the scale factor grows. No, I'm not going to go through the mathematical derivation. We're running out of time and I'm running out of voice. So just say it grows proportionally to the growth in scale factor. So you start at a scale factor of about 0.0003. You end at a scale factor close to 1. Oh, growth in amplitude by a factor of about 3,000. So 3,000, it's non-trivial, to be sure. But a molecular cloud core today has a density 10 to the 12 times the mean density of the universe today. The Earth's atmosphere has a density 10 to the 26 times the mean density of the universe today. You have a density 10 to the 29 times the mean density of the universe today. These extremely high densities, the densities at which chemistry flourishes, cannot be reached by gravity alone. Gravity is just not enough. Why baryonic matter is special is that it can radiate away energy. I am radiating away energy at the moment because, surface temperature over 300 Kelvin, I'm radiating away infrared photons. And so baryonic matter radiates away thermal energy. I maintain my thermal energy by eating lots of food. But, if you don't have a supply of energy in the form of chemical reactions or thermonuclear reactions, then it can radiate away its energy and collapse. So a blob of baryonic gas can be supported in hydrostatic equilibrium, same way a star is supported in hydrostatic equilibrium, if it's smaller than a length known as the Jeans length, named after James Jeans. If you Google James Jeans, be careful. There exists a clothing company specializing in the manufacture of denim trousers called, yes, you guessed it, James Jeans. So again, it's the distance traveled by sound during the time that the gas blob would collapse without pressure support. So for something, here I'm scaling to typical properties of the interstellar medium in our galaxies. If it's an object smaller than 900 parsecs across, it's nice and safe. It's stabilized by it's stabilized against gravitational collapse by building up a pressure gradient. So, okay, at the end of the Dark Ages, temperature was about 85 Kelvin, about one hydrogen atom for every 100 cubic centimeters or so. So small objects would have been safe against collapse. Larger objects, though, would have been able to collapse under gravity. And here I'm showing you the real James genes. So a sphere whose diameter equals its Jeans length has a mass of about 100,000 times the mass of the sun, scaling to those early temperatures and densities at the start of the Dark Ages. So a gas cloud bigger than this will collapse. It'll drive up the density, increasing. The density means that as long as it can radiate away the energy that it gains from adiabatic heating as it's compressed, it will keep cool, the Jeans mass will decrease, it will fracture to form smaller objects, but those objects in turn will collapse under their own gravity. If they can cool, they will become much larger than their Jeans mass, they'll fragment again. So if objects in the universe can keep cool, they will collapse and fragment to form small objects. If we look at a molecular cloud core in our galaxy today, it radiates away photons. It has dust, that's why they look dark. It has, today, carbon monoxide molecules. The CO molecule has a nice permanent electric dipole, and thus as it rotates, it emits microwave radiation. Now, a gas cloud made up of atomic hydrogen, atomic helium, and molecular hydrogen, it's not as good as not as effective at emitting radiation. So before you create stars, you have this problem that molecular gas, a gas cloud made up of molecular hydrogen, and atomic helium, isn't good at radiating away energy, and it isn't good at collapsing. That poor molecular hydrogen atom, it's symmetric, unlike the CO molecule, it has no dipole, it emits only feebly. So looks like you've got a problem. You had baryonic gas during the Dark Ages. It wasn't able to cool, wasn't able to collapse and form dense stars and dense planets and dense people. So how did it do that? Fortunately for me, stars enter next week. However, a possible spoiler alert is that the first stars that ever formed in the universe, when it was about 400 million years old, might have been very massive, and thus might have made these really, really explosive, not merely supernovae, but hypernovae, filling the universe with carbon and oxygen and nitrogen and so forth, and thus seeding the next generation of stars. But it does bring forth the fact that, you could make molecules during the Dark Ages, but it was really difficult. And the great gift of stars to the universe is providing new types of atoms. It's not just hydrogen, helium, and a smidge of lithium, with which you can do really interesting chemistry. So I'll stick around for a while if you have questions, but my big piece of advice, if you're thinking of going into cosmology, don't do it for the money. You should do it, of course, for the signing bonus and for the adulation of all those cosmology groupies out there. Anyway, thanks for listening to a cosmologist, and I hope you enjoy the rest of the astrochemistry series.
Thank you very much, Barbara, for the great lecture. So now time for questions. So you can write them in the chat or raise your hands. And so there are already questions in the chat.
Oh,
Can you
yeah.
read them, Barbara, or you want me to read them?
Well, so many questions. The greater abundance of baryonic matter over antimatter. Yeah. Now, I've been talking about protons and neutrons and free electrons, but I've been snubbing the antiprotons and antineutrons, which is an important part of the initial conditions for the universe. Unfortunately, that goes back way to the really early universe. However, short answer is if you have a very slight imbalance between matter and antimatter early in the history of the universe, if you annihilate matter and antimatter, that gives you, of course, a great burst of photons. And if there was just a tiny imbalance to begin with, then you have this tiny, tiny amount of protons and neutrons left over, surrounded by a large, large number of photons. Guess what? That's the universe we have today. Lots of photons in the cosmic background and only a few protons and neutrons. The question is, how you get that very slight imbalance to begin with. A lot of speculation about that, but still speculation. So if you want your Nobel Prize, that's a good problem to work on. Typical.
So there are two questions earlier than this one.
Yeah, I'm just starting at the end. So let's scroll up.
Starting from what kind of models are used to simulate the fusion pathway curves shown against time?
Okay. Yeah, so I showed.
If you want, I can read the questions.
Yeah, there are so many questions. Why don't you pick the good ones and I'll answer the ones you feed to me. So fusion pathway is time. That's really a great question because the Big Bang nucleosynthesis pathways I showed you are calculated, but you need to know, as I mentioned, cross sections for interactions, and you need to know the cross sections at the energies that were relevant for Big Bang nucleosynthesis. So people who do fusion today, are trying to create fusion in the lab. They're trying to create commercial fusion. They're looking at densities and temperatures that are quite different than those that were present at Big Bang nucleosynthesis. So it involves a lot of extrapolation. And to be honest, some of the cross sections used in Big Bang nucleosynthesis calculations are the result of extrapolation. So people, even in the time that I've been interested in cosmology, 30 years or so, they've been changing the numbers that go into these calculations because the laboratory astrophysics, it's been evolving with time. So it is an active field.
Okay, the next. You claim that the electromagnetic energy density scales with a to the power -4. This seems to be to violate energy conservation. Your argument hinges on the change of a photon wavelength with a, but you need to count the number of photons also, don't you?
Yes, you do. And yep, you found me out in that. In one sense, I've pulled a fast one on you. I assumed that photon number was conserved. And of course, you go outside, the sun is a glaring example of photon non-conservation. It's creating photons and sending them out into space. However, I was talking about the era before stars first formed. And also, I pointed out, stars are horribly inefficient. They've boosted the helium fraction of the universe a little bit, but only at the 10% level. Similarly, stars have boosted the photon energy density of the universe, but only at about the 10% level. The majority of the photon energy density of the universe today is still in the form of the cosmic microwave background. And when you go back to before when stars formed, in fact, the idea that the number density of photons goes as 1 over a cubed works very well. We're talking about the era when you had photons constantly being created and destroyed, for instance, by pair production. But, overall, statistically, you're not having a net formation or destruction of photons. Now, as you point out, yes, as a radiation-dominated universe expands, the volume of any portion of space expands as a cubed. The number of photons in that space is constant, we can assume. But, oh, wait, the energy per photon goes as 1 over a cubed. So where did the energy of those photons go to? And the short answer is, in general relativity, energy is not a globally conserved quantity. If you think of putting photons in a mirrored cube, expand the cube, you can say, oh, as the cube expands, the photons are doing work on the walls of the mirrored box. So in a finite box of photons, you can explain it away that way. But in an infinitely large universe, or in a positively curved closed universe, where does the work go? The problem is, it's an ill-posed question in general relativity. In Newtonian physics, you can talk about it going into gravitational potential energy. That's not a concept that works in general relativity, at least not on cosmic scales. So, yeah. Also, you can ask, same sort of question, in a lambda-dominated universe, the cosmological constant has an equivalent energy, and you are creating more lambda as you expand the universe. So a lot of questions in GR just don't make sense using classical concepts. But this is getting a long way away from molecules, but I love it anyway. Hand me another question.
Okay, is it possible that expansion of the universe is both speeding up and slowing down in phases? Speeds up, reaches a maximum, and then starts to slow down, reaches a minimum, and then the cycle repeats just like a wave.
It is possible. I've been saying, oh, the universe is observed to have its expansion accelerating today, and it is consistent with its being due to a cosmological constant. Okay, however, the study of what's making the universe expand today, dark energy is the term, is one of the most active fields of cosmology. It could be that dark energy is, as you're implying in your question, something that doesn't stick around. So you can think of, for instance, dark energy that decays into massive particles. That's within the realm of possibility. In that case, you're taking something that makes the universe speed up its expansion and converting it to something that makes the universe slow down its expansion. Now, how you make a universe slow down its expansion and then start its expansion accelerating again, you can in theory think about that. And in fact, we're going way off course here, but let's do it anyway. You can think about an era of inflation in the early universe as being a temporary cosmological constant, makes the expansion speed up, and then the dark energy that makes inflation happen decays into particles. And so the whole thing, in theory, could be happening today at a much lower level of energy density with the cosmological constants that we see today. So yes, it's possible.
Okay, the next. What are the background radiation temperatures of the ISM, dense molecular clouds, and cold regions?
Okay. So if you're in a dark molecular cloud. And let me just share my PowerPoint again so that I can go back to look at the molecular cloud. Okay, the molecular cloud core looks dark to us because it contains dust. I mean, literal dust, small solid particles made up of, iron silicates, probably coated with ice. Within one of these molecular cloud cores, light, as you see here, doesn't penetrate very well. So in the center of one of these molecular cloud cores, the heating is in many cases actually done by cosmic rays that penetrate to the center. And so the temperature in one of these molecular cloud cores can be as low as 8 Kelvin, but it's a balance between heating by cosmic rays and the radiation of photons, as I say, either from the dust, not very effective at 8 Kelvin, but there is some thermal radiation, and from its molecules, primarily carbon monoxide molecules. But there are lots of different phases of interstellar gas, each with a different heating and cooling mechanism going on. So, but I'm sure
You
you'll
will have, so there will be a lecture of Xander Tillens about astrophysical environments and conditions, and
yeah. So you'll get a lot of information from that about that from Xander Tillens, who's one of the world experts. I should probably zip my mouth up because I know a lot less than he knows.
Don't eat his bread. Okay, so I can continue. So if you still have time and
I have time.
okay, so then what is wait, no. Yes, what if density and critical density is same in our universe? Is there any possibility that our universe is non-Euclidean?
Yes, there could be some curvature to our universe. Remember, I expressed it in terms of this density parameter, the ratio of the actual mean density to the critical density today. And there was some wiggle room, it could be about 0.5% higher than 1, 0.5% lower than 1. So there could be overall curvature to the universe, either positive or negative, but it's so subtle that we haven't yet measured it. Now, the question of why the curvature is so subtle is one, of course, that's been asked frequently by cosmologists. And that's one of the reasons why this idea of cosmic inflation, accelerated expansion in the early universe, has been hanging around since Alan Guth proposed it in the 1980s. Because if you have a period of accelerated expansion, like the one that we observe around us today, it does have the property of tending to flatten out the universe. So, short answer, yeah, there could be some positive or negative curvature, but it's being flattened out by the accelerating expansion today, and we don't know whether it's positively curved or negatively curved.
Okay, the next. Could you address the great abundance of baryonic matter over baryonic antimatter?
Yeah, that's the one that we were discussing earlier.
Yeah, right.
It's the result of a small imbalance early on, but what that small imbalance was caused shrug.
So then what's the typical decay time of helium hydrogen plus?
Well, it depends upon the density of stuff surrounding it. So I think if you have helium hydride plus in isolation, it just sits there. It's cool. But as soon as it contacts any other atom or ion, it's very highly reactive. So
the next, how distance lead to redshift in photon wavelengths?
I'm sorry, I didn't quite catch that question. Let's see if I can.
How distance leads to redshift in photon wavelengths?
Oh, it's the increase in distance, that leads to the increase in distance, the expansion of space leads to the increase in wavelength of light, if you think of light as a wave. But flipping to light as a particle, longer wavelength leads to shorter photon energy. Photon energy goes as 1 over wavelength. So astronomers frequently refer to distance in terms of redshift. If you ask an astronomer, how far away is that particular galaxy, they will say, oh, its redshift is 0.36. So they will say how much the light from that galaxy has expanded in the time it took to come here. To convert from a redshift to the distance to the galaxy, you need to know the expansion history of the universe since the photon was emitted. So you need to know how much dark energy and matter there was. And to translate that into a distance in units of megaparsecs, you need to know the value of the Hubble constant, which we do sort of. So any redshift for a galaxy can usually be measured very, very well. There's quite high precision. But translating that into a distance, you have to deal with the uncertainty in our models for the universe, and in particular, the fact that embarrassingly, there's still this Hubble tension of not knowing how to translate from redshift to distance.
The next. So are there any models regarding whether lithium hydride could form aggregates, dust particles, as the temperature of the universe decreased during the Dark Ages?
No, this I don't know. Because there's so little lithium, everybody assumes that, it doesn't play a significant role. Yes, it can collide with hydrogen to make a lithium hydride plus ion, but the distance between any two lithium atoms or any two lithium hydride molecules is so immense that I'm doubting that you will get aggregates. However, I'm just talking off the top of my head and haven't done any of the calculations related. So I'm just assuming that the people who do this sort of thing for a living know what they're talking about. Sometimes a dangerous assumption, but not usually.
The next question. How does it come that we enter the area of lambda domination now? Do you think this is by chance because of anthropic principle, or might be a hint of observational flaws?
Now that's an interesting question that has occupied many people. When I showed you the plot of scale factor as a function of time, you would notice that, the time when lambda started to dominate at a scale factor of 0.77, it's kind of close to the scale factor now, which is 1. Now, you could say that if lambda had dominated very early in the history of the universe, there wouldn't have been time for galaxies and stars and planets to form. So there's that anthropic argument. You can't have lambda dominated very soon and still have a universe with life like us. However, why lambda started dominating in the recent past as opposed to the near future or the far future, that is something of a coincidence. And again, you could either say, it's some sort of anthropic argument as to why we are in a universe where lambda domination started so very recently. But, you could say, I don't know, it's the observations. It could be that we're in a universe where lambda will decay and you go back to matter dominated, as I mentioned in an earlier question. The problem is we just don't know. We just can observe the universe around us, observe its properties. After that, then you start asking these interesting questions. I just don't know.
The next, according to the Big Bang nucleosynthesis, most collisions shown in the presentation are binary in nature. Do you think three-body collisions are also possible?
Yes, but only in extreme conditions. So jumping the gun a little bit to stellar nucleosynthesis, I don't want to take away Professor Olofsson's lecture, but in the heart of a star, once you build up enough helium, if you collide two helium-4 nuclei together, as I mentioned, beryllium-8 is very unstable. However, in a very, very hot, very, very dense medium, like the core of an evolved star, if you have two helium nuclei close together as this very unstable beryllium-8 nucleus, if another helium-4 nucleus comes along, you can have what is effectively a three-body interaction, making carbon-12 out of helium-4. But, the time window during which this can happen, you have to have the two helium-4 nuclei in this very brief-lived state when the third one piles in, means that this triple alpha reaction, as it's called, happens only in the extremely dense, extremely hot cores of evolved stars.
Three more questions, if you don't mind.
Not at all.
Okay, could you please share your perspective on how quantum effects are relevant to astrochemistry and astrobiology?
My thoughts, I do not spend my time thinking about quantum effects in astrochemistry and in quantum biology, so I got nothing.
So you have to address this question to the next lecturers.
Yeah, that's a better idea. You should talk to somebody who knows more about quantum chemistry than I do, because I
Okay.
know zero about quantum chemistry.
Could the Matthew effect will be related with the baryon asymmetry problem?
I'm guessing not, because the Matthew effect, it's something that Isaac Newton knew about. He knew that in a universe that was almost of uniform density, the denser regions would collapse to form stars, for instance. But he only mentioned this at a qualitative level. But it is a very classical Newtonian thing. Whereas baryon, anti-baryon asymmetry, that's a very quantum thing, I'm guessing. So I can't think of any way to tie those two concepts together.
What is the universe expanding into? Is it more a philosophical question or physical?
Well, no, it's a geometrical question. For instance, a lot of cosmologists use the two-dimensional example of a two-dimensional universe being like a balloon being blown up. And in that case, the two-dimensional universe is expanding into a third dimension. So you can think of a universe with three spatial dimensions like ours, expanding into a fourth dimension. Okay, but my more geometrically inclined friends, that is, people who know about geometry in multiple dimensions, say, well, the expanding of an n-dimensional space does not necessarily imply an n+1 dimensional space that it expands into. You can think of the space being on its own and not needing a higher dimension to expand into. However, you should not think of the universe as being, a thing that is expanding into. Shouldn't think of the universe as being a finite three-dimensional thing expanding into more three-dimensional space, as the universe includes all of the space that there is by definition. The problem with discussing these almost philosophical questions is that discussing them in words makes you sound kind of wishy-washy. No, there is no more space because space is all there is. And I'm not sure that last sentence even had any meaningful content.
Wait a second. Do you think that early universe neutrinos are still present and can be detected?
I think they're still present. Detecting them, though, is going to be a real problem. The energy per neutrino in the cosmic neutrino background will be similar to the energy per photon in the cosmic microwave background. Not identical, because neutrinos are fermions and photons are bosons, so they have slightly different statistical properties. However, when people detect neutrinos, like neutrinos from the sun, or high energy neutrinos, presumably from active galactic nuclei, they're detecting neutrinos with energies of millions or billions of electron volts. And the neutrinos of the cosmic neutrino background, energies more like 1,000th of an electron volt. Since the cross section for interaction of a neutrino with baryonic matter is strongly dependent on energy, the itty bitty teeny tiny cross sections of these low energy cosmic neutrinos that we think are out there, that have to be out there if we know anything about neutrino physics, there's such a tiny cross section that people haven't yet been able to find out any really useful way of detecting them. Yeah.
One more question.
Okay.
Does the cosmic background radiation contain information about the molecules present in the early universe?
Again, if you're talking about early universe, like the time of recombination, we've seen that at the densities present back then, the number density of molecules would be low, like one hydrogen molecule for every 10 million hydrogen atoms shortly after recombination. So with such a low ratio of molecular hydrogen to atomic hydrogen, and with hydrogen molecules having only a weak quadrupole moment for interactions through their rotational properties, it's a case of the old joke, the food is terrible in such small portions. The hydrogen molecules are so bad at interacting with photons, and there are so few of them, I'm not certain they would produce any sort of detectable signal at all.
Okay, then the last question. The
Okay,
expansion of the universe. I mean, remember, I'm talking to the participants that we have a Slack channel, and so you can continue thinking about questions and send them to the channel. And then. So the expansion of the universe is primarily due to dark energy. But what is the role of gravitation?
Well, the expansion of the universe is due to the fact that the universe is expanding. So the fact that the expansion is speeding up now is due to the presence of what cosmologists generally call dark energy, which is just the term for whatever it is that's making the universe accelerate its expansion, and which is consistent with being the cosmological constant first introduced by Einstein into his field equations in 1916. So the cosmological constant is part of gravity, but it's part of Einstein's gravity. It's built into general relativity. There's no real equivalence to a cosmological constant in Newtonian gravity, which is why, at least for old-fashioned Newtonian physicists like myself, it's very hard to internalize what the cosmological constant is actually doing. I try to think of it as, it's exerting a force outwards, but that's just falling back onto Newtonian language for what is an intrinsically relativistic concept. So the idea of an expanding universe, yeah, that's something you can deal with in both Newtonian and relativistic physics. But the idea of the accelerating universe, the expansion speeding up because of either a cosmological constant or some similar idea, that's really a general relativistic concept. So it is gravity, but it's specifically GR gravity.
Okay, so many people write you, thank you very much, and great lecture and amazing lecture. And I just join this core and say thank you very much, Barbara, for the lecture and the answers and the patience and the knowledge.
Well, thank you for having me, and I'll be handing in my lecture slides. So anybody who
Yes,
wants
send
to,
them, please. Yeah.
And my email address is also on the first slide. So if you have any cosmology questions, just send me a quick email and I'll answer them as quick as I can.
Okay, thank you and take care.
Thanks. All of you, take care and enjoy the rest of the course.
Thank you.